Welcome to Walk About the Galaxy, the fired up astronomy podcast, where the science is universal, the opinions are personal, and the topics are spiral, meaning of, about, or pertaining to spires. Right?
Sure.
We are Strange Charm atop the Astroquarks, also known as Josh Caldwell.
Addie Dove.
And Jim Cooney.
Coming to you from the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. We are also on the World Wide Web at walkaboutthegalaxy.com, where you can see how to order a Walkabout shirt and support STEM education at the same time. If you order a shirt or you have any questions for us, feel free to send an email to WTG, which is one better than WTF, at ucf.edu. Our stumper today is exotic locational.
Ooh.
Which is of, about, or pertaining to exotic locations, Jim.
Right on.
Checks out.
You're going to spend 1 month making scientific observations and carrying out data analysis, basically being some sort of observational astronomer scientist for 1 month at one of the following two locations. Which do you choose? The South Pole Observatory, where we have the Atmospheric Research Observatory monitoring the Earth's atmosphere, and the Martin Pomerantz Observatory carrying out astrophysical observations, and the Ice Cube Observatory, which takes a careful look at rappers and neutrinos.
Like Ice Cube. Yeah.
It's at an elevation of 2,800 meters, and it's at the South Pole, coincidentally. Or the Mauna Kea Observatories on the Big Island of Hawaii, where there is a large number of optical and infrared or near IR observatories, but you may not descend below the base camp for those observatories of Hale Pahaku, which they call HP, which coincidentally, or is it, is also at 2,800 meters above sea level.
Okay, what are the options? There's a lot of words. Mauna Kea or Antarctica?
South Pole.
Great.
It's the South Pole Observatory Stations.
And how long are we there?
A month. 1 month. Or HP and above on Mauna Kea for a month.
Do you have a permanent supply of ink? That one too. Sorry.
I don't get it.
HP.
I just keep thinking Harry Potter for some reason.
I don't know why you would think that.
I'm going to the South Pole.
Are you?
I am. It just seems more unique. Like, it would be cold. I mean,
You're probably not going outside much.
No.
They got those big fluffy coats.
I mean, I don't know what season. I mean, obviously, some of these aren't optical telescopes, so you could do this in summer, some of these things. But I'm going to assume I'm going to go in the middle of winter.
Most people go in the summer.
I'm going in the winter.
Okay.
Because...
So, total darkness.
Total darkness. For one, I've never seen the northern or southern lights, and you might be able to see right at the South Pole if you get a good glimpse of it.
Yeah,
I think
maybe not, but you would see a completely different night sky.
Yeah, totally different night sky. It was really, really dry, really dark. Obviously, also at the top of Mauna Kea. I mean, that's why they put observatories there. But it would just be, I think, very unique and interesting. And then you could say you were at the South friggin' Pole.
Right.
A lot more people can say they've been on
Mauna Kea.
It's true.
What do you think?
South Pole.
Also.
I've been to Mauna Kea, and it's cool, but I would like to hang out with Jim.
Okay.
But I would love to go to the South Pole. I would love to do the ANSMET, the meteorite search, also in Antarctica.
Okay.
And I have some friends.
I don't know if you'd be able to do that during this particular stay.
No, I wouldn't.
Yeah,
I wouldn't. But now I have some friends who have done research down at South Pole, and it just seems awesome.
At that South Pole station, they've got a clear air zone set up where no
farting
activity. That's not the only thing that's not allowed. And there are people who they'll get detailed there for a full year.
Yeah, the people who winter over.
Yeah, and they're there for 9 months by themselves.
Yeah,
and 6 of those months it's dark.
Dark. DARK.
Yeah, so, that would drive me. See, the thing is, it was only 1 month. Like one month, I could, because you always see the end of that, right?
Yeah.
Like, okay, 2 more weeks, 3 more, whatever. But like,
even if it's very dark, you can see the end of that.
Yeah. But I think, holy cow, I would get really depressed and stuff if it was dark.
Yeah.
It's not even the cold that gets me as much as the
I'm
dark.
not even sure how I would do for 1 month of total darkness. But anyway, well, I guess you'll both be going to the South Pole soon.
Yay!
Since the Stumpers are actually they're totally non-hypothetical actual
sweet.
choices
We get to go there.
that you both get to do every time. Yeah.
Yes.
Well, today we'll talk about finding the culprit of the dinosaur extinction, or whence it came, Saturn's sludge-like interior, and spiral arms in the Milky Way. But first, this episode of Walk About the Galaxy is brought to you by mRNA. If you're feeling amorous, send a bouquet. If you're feeling whimsical, send an e-card. If you're feeling generous, send some financial help with any number of apps. But if you'd like to tell your body's immune system how to create a top-line defense against a novel coronavirus, use messenger RNA. Don't be fooled by this molecule's single strand. Its nucleotide sequence has all the information your body needs to armor up and keep foreign invaders at bay. Send a message to your cells with mRNA. Messenger RNA, when it absolutely, positively has to be there overnight.
Gotta give props out. Thank you, mRNA.
Yeah.
They have not just for sponsoring the program, but also for being a huge help and
Vaccines.
trying to tamp down.
Not the one I got.
No,
you didn't get the
yeah.
Oh,
Andy
neither
and
of
I
you.
both got the Johnson & Johnson, which is not an mRNA
It's not.
vaccine.
Yeah. Well, they didn't.
But this is the first major thing that has gotten an mRNA. I mean, they've been working on those things. I mean, everybody was amazed at how fast they went, but really, they've been working on this basic concept for a decade.
Right.
Yeah.
And this is the first time we really got to test it out, and it worked phenomenally well.
Yeah.
Yeah, I can't remember the adjective that goes with the kind of delivery system for the Johnson & Johnson. Starts with an A, I think. But in any event, maybe they'll... I'm open to you guys for sponsoring if you want to reach out to us. Yeah.
Is it FedEx?
It is FedEx.
Okay.
I thought that was going to be super obvious, but it's old FedEx. It's sort of pre-year time FedEx, because it was revolutionary at the time.
Yeah.
That you could make
Get
sure
something
that
there
something
overnight.
would be there the next day.
I recently shipped something via FedEx, so I appreciate the sponsor, the shout out.
Right. I think I've mentioned this before, but there was a time when you'd print your proposals to NASA.
Yes.
And you'd have to send 15 copies, and they'd all have to have signatures, and it'd be this box of, these sort of 50-page documents stapled together, and they had to be received at NASA headquarters by a certain time and day. Mm-hmm. And people would get up against that deadline. One of my colleagues once flew and personally carried his box of proposals
because it was cheaper than, or because you couldn't ship it overnight.
He couldn't ship it overnight
back then,
and
you couldn't email it.
He had to take them there because if he put it in the mail, it would get there in 2 or 3 days. And he went to the Denver airport, and got on a plane with his box of proposals, and flew to Washington and handed them. Then took a cab to NASA headquarters, said, "Here are your proposals."
Wow.
On time. Yeah.
Wow.
Maybe it was even the same day that he got the thing. I don't know if that proposal was selected.
I hope it was.
I really hope it was. Yeah.
But it probably wasn't.
I don't know.
Selection rates were better back then.
Yeah, I'll have to ask him.
Yeah, I'll
find out. I've got a rant.
Oh. Is this a?
It's disconnected from absolutely everything.
Okay.
Random rant.
The random rant is: do you ever get emails where it's sent to some list of people whose identity you don't know because they're all BCC?
Yeah. I also get lists of emails that aren't BCC to 500 people, and those are also terrible.
Those are worse in a different way, but also terrible, deserving of their own rant. But these emails just sort of say to whomever sent it, and the actual recipients are a mystery. And then the content of the email says, "Hi, could you please give me this information?"
Uh-huh.
Lots of people have that information.
Okay.
Has this email been sent to all of those people? And then all of those people are going to
I feel like this is a very administrative rant.
No, you've never had this happen?
No.
Seriously? Where you get an email and you're like, do I need to answer this, or am I only receiving this as a courtesy copy? Like sometimes it's just because hey, this is just for FYI. We're doing this. And other times you're the person who's supposed to do something, but you have no idea whether you're this person who's supposed to respond to that or not.
I don't think this is a big problem in my life.
Do you default to giving the answer? No.
I scream at the computer is my default.
I don't think this is a big issue in my life. I think
Lucky you.
this is more of an administrative issue.
Yeah.
Because it's a recent rant, yeah?
No, I've had this before,
Okay.
But I was still in an administrative position prior to this one. So in any event, please, administrators and people sending emails to say,
Mystery
like,
people.
I'm sending this to
Department
this group.
chairs.
For example, I'm sending this to department chairs, and I'm also copying in whomever. All right, whatever.
Okay. Wow.
I'm getting no
that was
sympathy
such a
on
great
that rant. Very angry
It's okay.
about it.
Do you want to rant about how you didn't get sympathy on your rant?
It just bugs me.
You know what really grinds?
You know
my
what?
gears?
You know what else
Sorry.
bugs somebody?
A lot of things.
NASA selecting SpaceX and not selecting Blue Origin. That really bugged Blue Origin.
And Dynetics. They're still involved in it, I think.
Okay.
To do what?
Well, but Blue Origin filed a lawsuit against NASA.
I think Dynetics was involved in the lawsuit also.
Okay.
They were involved in the original petition.
Explain.
So this
I
is
have no
about
idea
the
what you're
human
talking
landing
about.
system, which NASA had. There were several companies in competition. NASA selected SpaceX. Blue Origin and Dynetics filed a complaint. Blue Origin is getting most of the press for it, but they both were involved in the complaint about how the process was done.
And they failed that.
And they basically failed it. The review came back like, nah, it was fine. They said they were going to select up to so many. They could have just selected none. Right. The fact that they selected this one is fine, and the budgeting stuff wasn't that sus.
Right. So now they filed a lawsuit.
Yeah. Which sucks because it means that like NASA can't move forward with SpaceX.
They have to
like pause work to move, and they can't move forward. Yeah. Like I understand there was, I think there was a good article I read that's basically like, I mean, from Blue Origin's perspective, you could totally understand why getting cut out so early is painful. Because like SpaceX has done as well as they have because they got an early contract from NASA, right? In the early COTS program to develop crew and cargo.
Right.
And they've done as well as they have because of that.
Right.
So you can understand, but the thing is, like NASA has said, we will pick other companies in the future. We will have this competition again, basically. So it's a little bit like, okay, and we get it, but and they're putting out all these like stupid graphics.
Right.
It's just not a good look.
They're doing some PR. They're doing a PR push, and I think you can say what you've got going on with Blue now.
Yeah,
publicly.
I'm flying with them next. Well, I'm not flying. My payload is flying with them next week on a New Shepard rocket.
The 17th flight of New Shepard, as I understand.
I think that's correct.
NS.
They have there's the different numbers because like I'm a payload, so I'm P11.
Yeah.
But I think it's NS17. Yeah. They have announced it publicly.
So that should be
there's 19 payloads on there.
Right around the same time that this podcast airs.
8 a.m.-ish Central on Wednesday.
Yep. Nice. Good luck.
Thanks.
Hope it works.
Me
exciting.
too.
Yeah, and you get to spend some time in Van Horn. So even if it doesn't work, it's
a win-win.
It's a win-win.
I'll get to see my stepsister and her family live in El Paso, and so now they just moved there.
Okay.
So I'm flying in and out of there, so I'll get to see them.
Alrighty. Well, the Starliner is, speaking of rocket troubles, the Starliner is back in the garage. Its valves are sticky or something like that. So this is Boeing's crew capsule to take astronauts to the space station, and it was out there on the launch pad, in principle, hours away from launching, and they were getting some unhappy
I think not even hours.
From some valves.
Yeah, those valves.
At first, frequently, I remember in the shuttle days, frequently the bad readings were not the thing was actually a problem, but the sensor that was providing the reading on the thing was giving an incorrect report. So the thing wasn't stuck. It was just the thing looking at the thing
you just
that was stuck.
Stay in the bathroom longer. It'll work.
The valve stuck.
Sticky valves.
Sticky valves.
Minor problem.
But it probably is something worse.
I don't think I want to have any elaboration on that. Actually.
But it probably is something worse, which is unfortunate.
But unfortunately, so it's back in the garage. So we'll have to keep an eye on that. It's going to be a little while because the Lucy launch, I think it's been pushed to after the Lucy launch.
It has, because they're going to use the rocket, the first stage, I think they just like left it there, so Lucy's going to use it or something. Okay. I was surprised that they could just swap them out anyway. Like that. So
for Atlas, it's an Atlas. Anyway, it's a ULA rocket.
Yes,
I think for all
and
future,
Lucy is a mission that's going to the asteroids near Jupiter.
rocket talk, you have to begin
with a description of what the hell we're talking about.
The statement of which company you're talking about.
We've been saying most of those things.
United Launch Alliance.
Okay. Yeah. You have to have a title, and then you do the things. Because I get lost easily. I'm not.
But a title doesn't help you not get lost.
Yeah. If you say, okay, Blue Origin news.
But we included like 6 companies in that discussion we just had.
Yeah.
Okay.
We said it all.
And we said them all.
We said them all. Anyway,
Lucy's a space mission.
I just said it's a mission to the asteroids near Jupiter. Those are words I just said.
He did just say those words.
I am.
Yeah.
You were too busy telling us what to say and not listening to what we did say
about things.
Sorry.
And I was just setting up the beautiful segue to our first topic because since Lucy is going to visit asteroids a little bit further away
with diamonds
from the Earth than many asteroids, that takes us to a study about asteroids that hit the Earth.
That was a beautiful segue.
Nice.
Thank you.
It does. So sometimes asteroids hit the Earth. That's the title, Jim. Sometimes asteroids hit the Earth, and sometimes it's not a big deal if they're little tiny bits of asteroids, but sometimes it's a giant deal, like if it's Chicxulub, which is the...
We totally pronounced right.
Yeah, which is the dinosaur killer, the site of where the dinosaur killer impact occurred, and the site of much study. And there's also much work that's done, right, to try to figure out where that asteroid came from. We want to sort of know, we're very curious these days, especially like when is an asteroid going to hit us and what will the impact be?
The consequences.
What are the consequences and the actual physical impact?
Right.
And it's a pretty complicated question because it turns out there's lots of asteroids in lots of different orbits, and they don't just stay on one orbit. They move around. So most of the asteroids we study for potential Earth impacting orbits are near-Earth asteroids, NEAs, or sometimes NEOs if you are saying near-Earth objects instead. A little bit more inclusive category.
So does that just mean an asteroid that has a path that crosses into the inner solar system?
It's not just the inner solar system. It's like that it has within a certain range of Earth's orbit. Yeah. Okay. So some of them actually do cross Earth's orbit, but some of them are just like in the range of Earth's orbit.
Yeah, there's all these subcategories for NEAs like the Apollos and the Amors and the A10s. And so sometimes it's like how their semi-major axis or their average orbital distance compares to the orbital distance of the Earth from the Sun, and whether it's eccentricity of the orbit, whether it's whether the orbit actually crosses in distance the Earth's orbit or not. If it's just coming close. So you have those different sorts of subdivisions.
Yeah. And a lot of the meteorites we find and the remnants of asteroid impacts on Earth are from ordinary chondrites. So... yeah, they're just ordinary. They're probably called that, right? Because we found a lot of them at some point. I don't know. But it seems like other studies have shown previously that probably the source of the impactor for Chicxulub was a carbonaceous chondrite, which is a different type of material, obviously more carbon. And so that maybe tells you it comes from slightly different areas of the asteroid belt potentially.
Usually further, colder areas, right?
Yeah.
And the carbonaceous chondrites, in my mind, I think of stuff that's more like crunchy.
Okay.
More friable, sort of more like styrofoam kind of.
We need to have Beauty Cork on to help us with this one, maybe.
But they're those outer things.
And darker
especially
oftentimes,
when they come in, they're weaker because there's more sort of volatiles that are acting as glue that helps hold them together out there. You bring them into the toasty inner solar system, then they just fall to pieces in your hand.
Yeah.
But if they're big, they're still going to kill all the dinosaurs.
Yeah, they're going to fall to pieces, but still smash and destroy your atmosphere.
Yeah.
So, not great.
Yeah.
So it's been hard to predict sort of so we know that there was an impact, but without knowing anything else, right, it's really hard to predict like what the source of that asteroid was, where it came from. So we use some of these things like knowing it's probably a carbonaceous chondrite, some other stuff we know about composition of other things we find in the layers of that impactor. And there's this iridium layer that we've studied for a long time, lots of things like that. And so, but there was recently a study done with all computer simulations. It was a dynamical study that was done by some colleagues, primarily at the Southwest Research Institute, to try to understand if it was an impactor that maybe came from the outer part of the main asteroid belt.
Main belt being between orbits of Mars and Jupiter.
Yeah. Right. So it's where it's the main belt because it's where a lot of the asteroids live.
That's where my asteroid is. That's where your asteroid is.
Exactly.
That's where all the good asteroids are.
That's where all the good asteroids are, yeah. So they did some dynamical studies, and the paper's interesting. It talks about how like there's a lot of different studies now that are trying to make predictions for when these asteroids will come into an Earth crossing orbit and where they'll come from, in whether they're NEAs or in their different parts of the main belt. But this study did sort of a narrowly defined thing where they made it a simpler model in some ways, where they sort of said, okay, we have the main belt, and they looked at all only objects that were greater than 5 kilometers. So it's thought that the Chicxulub impact was maybe a 10-kilometer diameter.
Yeah.
But there's only like 2 of those that we know of in the main belt. So like statistically, they broadened their sample and looked at asteroids that have been detected primarily with the NEOWISE survey to have greater than 5-kilometer diameters. There we go. Words are hard. And they looked at sort of their current statistics of their distributions, and then they did a bunch of modeling for those asteroids and their current orbits, and with some predictions about how those orbits change due to perturbations due to planets, but also due to thermal perturbations. So a lot of orbits get changed on asteroids due to the YORP effect. YORP.
Yes.
It's just an acronym. It's YORP, which is all four people who
sort of proposed it
in like a couple of different papers. Yeah. And they're all, I think, Russian, so I can't pronounce most of them. A bunch of them are Russian. Yeah. But anyway, so the YORP effect talks about what happens when you have basically thermal effects on asteroids, that there's radiation, sunlight shining on a dark thing. It heats up and it re-radiates that radiation, and it actually changes how it spins and what its orbit does.
It's sort of Russian, non-Russian, Russian, non-Russian.
Okay.
Yarkovsky, O'Keefe, Radzievsky, Paddock.
Okay, yeah.
What's fun about that is that another effect on those things is called the Yarkovsky effect, right?
Right.
Yes.
Which is different.
So it's different, right? A different effect. He was all about that
was
stuff.
all over that stuff. And it's really cool because it's just the radiation from these objects. They heat up and they emit radiation, but they do it anisotropically. So not all evenly. The invisible to our eyes radiation coming off these satellites doesn't all go off in the same direction. And it goes off and it carries a little bit of momentum with it, which means there's an equal and opposite reaction on the asteroid, which is unbalanced by the uneven distribution of radiation leaving. And amazingly, it pushes stuff, even big things, all over the solar system. If you give things hundreds of millions or billions of years, these little tiny radiation forces push stuff around.
Yeah, it's a big thing for asteroid studies. So people study how it changes the spin rates of asteroids. Right. Yeah. And there's some there's some nuance to like which exactly effect it is. And there's the binary YORP effect, which has to do with new binary partners.
Orbits of how
the orbits
things
change.
Yeah.
So it's pretty cool. And it's this effect that like people didn't include for a long time. You just sort of looked at generally what their orbits were going to be and how they're perturbed by other gravitational forces. But turns out YORP effect has a big deal.
There's also the Poynting-Robertson effect, which is also
mostly on smaller stuff.
Right.
Yeah, that
related
works.
to this. But so anyway, it's very cool. And it's partly what's responsible for bringing asteroids and meteorites to the Earth.
Yeah. And potentially in this Chicxulub impact. Yeah. So the study shows that you can get a much larger contribution from the middle and outer main belt of Earth impactors than previously suspected, previously modeled.
These YORP people killed the dinosaurs.
Yeah, exactly.
That's basically what you're saying.
Those YORPers killed the dinosaurs.
Well, speaking of things moving slowly, we'll do our trivia.
Okay.
As we transition to even further out in the solar system. Race walking, as you may know, is still sadly an Olympic sport.
I hope we don't have any Olympic race walkers as part of our audience.
I know.
They're going to
race walking
You'd be offended twice.
is the most exciting Olympic sport. And we just need more distances of race walking to be competing in the Olympics.
You overcompensated too far.
Okay. So in any event, if you ever, like you're walking, need to get somewhere in a hurry, you're sort of like, oh, do I walk or do I jog? You know, you're walking briskly, and it's like,
people in the mall.
It's like, am I actually even going any faster now that I'm jogging? Anyway, there's this sort of natural transition speed that we go from a walking stride to a running stride.
It's tricky on the treadmill sometimes.
Yeah. So you could try it out on the treadmill. You could sort of just gradually speed it up and decide, okay, when do I have it covered up and have somebody speed it up for you and sort of gradually say, okay, when am I going to change from walking to running? Yeah. Anyway, it turns out on Earth, for everybody, it's around 4.5 miles an hour. That's called the preferred transition speed, or PTS. And it has something to do with physics.
Ooh. What?
It's crazy, isn't it?
What?
But it has to do with the acceleration of gravity and the force they're acting on us. So there's, and our size of our bodies probably has something to do with it. So in any event, the question is, what's the preferred transition speed from walking to running on the moon? Since we're going to be sending people back.
Did we say what it was on Earth?
4.5 miles per hour.
Okay.
So they did an experiment.
Miles per hour.
They did an experiment on the Vomit Comet with 8 volunteers and 8 treadmills.
Nice.
And they put them.
I've seen treadmills.
Did they really test this?
Yeah, I've seen treadmills on the flights before.
So there's some physics with equations and things that gives a prediction, but then they tested it.
That's fun.
So there's 2 parts to the answer. There's what did the prediction say and what did the experiment say. Well, they had these people on the Vomit Comet try to walk while the airplane flew lunar parabolas.
Nice.
And gradually sped up the treadmill, just like you can try this at home at 1G if you got a treadmill or at the gym.
Yeah.
And at what speed do you find yourself wanting to stop walking and start running?
Okay.
So the question is, what is that?
Or just turn off the treadmill at that point.
What speed is that on the moon? If you were walking on the moon without having to deal with spacesuits and everything like that. So you're in a moon base. You're in your normal clothes, right? So that's your trivia.
Okay.
Yeah.
Wow. That's good.
Let's talk spiral arms.
Spiral arms. Let's go way the hell out there.
No, we're going to start with spiral arms and Saturn.
Oh. Nice.
Yeah.
Okay.
So
only a little bit past the main belt.
You may or may not know that I study Saturn's rings.
Do you?
Data from Cassini.
I don't know if our listeners have ever heard about that.
One of the things that I actually discovered that was discovered by 20 other people at the same time, but was additional funny little rings in Saturn's C ring.
Ooh.
Funny little waves. I'm sorry, not rings, but waves in Saturn's C ring, spiral waves. There's a bunch of these spiral waves in Saturn's rings, and they're caused by resonances with something. So something gravitationally excites or perturbs the orbits of ring particles at a regular frequency that is resonant with a natural motion that the ring particle wants to have as it's orbiting Saturn.
Somebody's knocking Saturn with a little hammer.
Somebody's knocking the ring particles.
The ring particles with a little hammer at the same time every time as they go around Saturn, kind of thing. Yeah. Perfect.
And when it does that at the right frequency, at a frequency that the ring particle likes to wiggle.
Those ring particles always wiggling.
Ring particles are wriggling and wiggling. Then that sets up a wave in the rings. And there are a couple of different kinds of waves depending on how that hammer hits those particles, what kind of wiggle it excites. Okay. Most of the waves are excited by the hammer. The hammer is gravity from a moon.
Right.
But then we saw all these waves in the C ring. Some were seen in Voyager data. Then we saw some in Cassini, and then some of my colleagues saw even more than I saw that I missed. But we saw some.
Yeah.
And there are no moons hitting those ring particles at the right hammer frequency.
Oh, no.
But it turns out that Saturn itself is acting as a hammer for those. So that means that the planet has some non-spherical aspect to it whose gravity acts like a hammer.
Interesting.
We're just going all in on this whole hammer
we got to be really careful about this hammer
it.
analogy because all I can think about right now is Dr. Horrible.
Oh.
And the hammer.
Sing-along song?
Sing-along blog.
Sing-along blog? Yeah.
There's a character called Captain Hammer. Anyway, it's fine. It's fine.
I remember Dr. Horrible vaguely.
Yeah.
But, I don't remember Captain Hammer. But anyway,
the hammer is his...
He's hammering things.
Yeah.
Anyway, we're hammering the ring particles.
Okay.
Turns out Saturn's interior has lumps. Or
yeah, so this
lovely planet lumps
is not... I mean, anything that spins and isn't perfectly solid will flatten out a little bit.
Right.
We're not talking about that.
We're not talking
that's still
about
pretty
that.
Not its oblateness.
That's not going to launch waves in the ring.
So what it turns out, it has to do with Saturn itself oscillating. And it has various natural frequencies of oscillation. And so you can sort of think of Saturn and all of its interior layers as like the surface of a drum.
Okay.
Right.
And if you imagine a surface of a drum and you hit it, depending on the tension of the drum and how you hit it, you can get various sorts of ripples. And maybe if you hit it regularly, you can set up standing waves in that surface, a little pattern in that drum head, depending on how frequently you hit it. So Saturn's interior does that, which produces this non-axisymmetric modes in the interior of Saturn, which then in turn act as hammers on the ring particles, which produce waves.
That's pretty fun.
It's just amazing you can do this, because first, the amazing thing is that all that happens, that it actually tickles those ring particles enough to make them wiggle in a way that we can see, which we can. And then you can take that and back out of it what the heck is going on in Saturn's interior.
And we really don't know what's going on in Saturn's interior.
Well, we know more.
We know more now, though.
We know more now.
Yeah, the models are really complicated.
Yeah.
It's hard to figure out what's going on in there.
So we have information. So first we got the picture of the planet so you can see what its shape is. Then you have the gravity, right? As you were saying, which we get a lot of information on from the orbits of the moons and the orbit of Cassini when it flew by, especially in its final dives in between the rings and the planet, so-called grand finale orbits, provide a lot of really interesting information about it. But now also the orbits of the ring particles themselves and the fact that they're being tickled in the right way, in a certain way, when this sort of pattern of waves also provides insight into the interior.
So what is it?
It is a diffuse, surprisingly large core.
I've heard that about Saturn.
I always think of Jupiter and Saturn as sort of like very similar, or maybe naively we do, or because we shouldn't, as it turns out.
They're not very much the same in the books sometimes. They're starting to get more.
Yeah.
In my
more
simple
different,
books,
more differenter.
They seem very similar. It's like they're mostly hydrogen, helium, and the outermost parts is just gas. And then if you go down far enough, the densities and pressures are high enough that it's kind of a liquid. And if you go down even farther, it's kind of a metallic liquid. And if you go down far enough, you find the core materials that the original planetesimal was made of, the ices and rock and metal. So when you say core, how much of that are you talking about?
Well, it's I'm not sure exactly what you mean by how much of that I'm talking about.
Meaning, are you just talking about like the ices, rock, metal stuff that's way down in there, or is core defined here by how I don't know how
solid it is?
So it could be defined by composition, and it could be defined by the material properties of it. So, like on the Earth, the core is defined compositionally,
right?
And the crust and the lithosphere overlap. One of them is defined by composition and the other is defined by brittleness. Right. In this case, I'm not 100% sure whether this is a purely compositional definition or not. But the core is big, 60% of the planet's radius, containing 17 times the mass of the Earth. So that's, to me, those two numbers are surprising, because Saturn itself is almost 10 times the diameter of the Earth. So 60% is 6 times the diameter of the Earth. Did I do my math there right? Which is...
They do say it's a somewhat arbitrary core definition at some point in the paper.
Well, there you go. So that's why I gave a somewhat arbitrary answer.
Yeah.
So in any event, that means that core is less dense than the density of the Earth as a planet as a whole.
Right. That is surprising.
Right, because 60% of Saturn, a sphere that size, has more volume than 17 Earths.
Right.
So it's less dense than the Earth, but it's much more dense than Saturn as a whole. You probably are aware that Saturn is less dense than water.
Saturn will float in a big cosmic bathtub.
Just be aware when you drain it, it'll leave a ring. Thank you, Jim.
You set him up for that one.
So in any event, it's a large, squishy core that's got a stably stratified transition from the core to the envelope.
It's got a nice ombre effect
above it. An ombre effect?
Uh-huh.
Just go with it. Is.
It's like a color transition thing that everybody does, right? Or
I don't know.
Oh, it is.
I have no idea what you're talking about.
I'll show you a picture.
What company is that?
Is she just like
first
much
before
younger
you say
and hipper than us?
Well, yes.
If you ask
I don't
Josh,
know if this has anything connected to that.
If you ask Josh at our last recording, we're all of the same generation. You said that multiple times. So
did I really?
You said if you're of our generation, referring to you and me and Phil, I think.
I was thinking I was
or
talking
maybe that
about
was
me
at a
and
different.
Phil.
I don't know. It was funny though.
Yeah.
Ombre design is where it like fades from one color to another kind of thing. Now you do. You should ask your wife about it.
Okay.
She probably knows.
Maybe so.
She's an artiste.
In any event, yes, it's very much that kind of effect. It's a shady thing. Somewhat related to this,
it's kind of like a lot of this discussion.
Is I mentioned those gravity passes that Cassini did.
Yeah.
They weren't really able to like figure out what the heck is going on in Saturn, the distribution.
It's complicated.
It didn't fit. They couldn't come up with a solution that fit the data that they were able to collect without adding in basically random accelerations to the spacecraft.
Oh, jeez.
Yeah. So we should totally go back to Saturn.
Yay.
Yes.
Yeah. But speaking of spiral waves.
So one of the coolest things about our universe is the fact that physics is universal and that the same physics operates on small scales as it operates on big scales. There's one set of physics for everything. And Saturn's rings, the total diameter of that ring system is 150,000 kilometers or something like that?
No, the diameter of the ring system of the main rings would be about 274,000 kilometers.
Okay, so a few 100,000 kilometers. The diameter of our Milky Way galaxy...
It's like 500,000 kilometers.
Slightly bigger.
Is 100,000 light years side to side. I know that from the Monty Python song.
Oh,
yeah.
I didn't know that.
It's 100,000 light years side to side.
That is how the song goes.
They knew that way back then, even.
Yeah.
Yeah.
But yeah, 100,000 light years, which is...
It's actually like closer to 160 now, isn't it? Didn't we have an update on that a few years ago?
Well...
Anyway.
Whatever. It doesn't... I mean,
it's big.
How you define the edge or whatever, but... Yeah. It's a lot bigger. It sounds similar because it's a few 100,000. This is when you don't know your units. You get yourself in real trouble.
Yes.
It's a few 100,000 somethings.
I tell you what, if you don't know your units, you're always going to be in trouble.
Yes.
Not just when you're talking about this.
Yes, that is true. In this case, of course, a light year is considerably larger than a kilometer.
True.
By a factor of...
several.
10 trillion or so. And so... But the same physics is happening, right? We live in a galaxy which is also spinning around, and much like Saturn's rings, it's a flattened disk of spinning material, and you get very similar physics effects happening in those things. And so we've been trying for many years to figure out, I mean, we can look out at the universe and see all these beautiful spiral galaxies, but when we look at our own galaxy, it's very hard to determine what the structure is, of course.
Because we're in it.
We're friggin' inside of it, right? And... that wouldn't be so big a problem, except that in addition to all of the stars that we can see, there's also a huge amount of gas and dust in our galaxy, and that gets in the way of seeing the stars behind it. And so we have a really hard time seeing what's going on in our galaxy. We would love to map out what's happening in our galaxy. What we find is that, we do have spiral arms, and the spiral arms, of course, are created in a similar physics way as those spiral waves that Josh was just talking about in the...
Yay. There's hammers out in the galaxy, too?
There's hammers out in the universe.
Right.
The hammers are very different. Instead of moons...
they're bigger.
It's still a gravitational hammer. It's just the source of that gravity is different.
That's right.
Yeah.
And we don't really well understand. We don't have specific explanations. I mean, many of the spiral waves in Saturn's rings, we have specific explanations for. It's this moon or that moon, or the weird interior of Saturn. For our spiral arms in our galaxy, we're not going to know, because they were kind of whipped up billions and billions and billions of years ago. We're not going to know the specific hammer, but we know roughly what's happening. It's,
but it's probably more like the waves we were just talking about with Saturn, where it's the interior of the galaxy being lumpy that's tickling it.
So for some of these things, in other, I mean, the very grand scale structure is probably other passing galaxies and things like that provide tugs that start a spiral wave. And of course, in Saturn's rings, these spiral waves, it's weird. It's kind of weird to even call them spiral. They look just like almost rings around the. Around
They're very
Saturn.
Tightly wound,
right? Because there's this thing called the pitch angle.
Like I am this week.
Right.
He said it.
For spiral things like spiral arms, there's a number that we use to kind of quantify how spiral they are. That's the pitch angle.
We like numbers.
0 degrees would be just a circle, right? And then a higher angle means further and further away from being a circle. And in Saturn's rings, they're all very, very close to zero. Yeah. And so they're very tightly wound spiral things, and you can't tell the difference between them in a circle very easily. For our galaxy, it's not so much. The typical arms in a spiral galaxy have pitch angles of 10 or 12 or 15 degrees. So that's how close to being, kind of tangent to a circle those things are. But there's a cool recent paper out there where we found smaller structures. So the big spiral arms, but there are also little smaller structures. And we found a really cool small structure not too far from us that has a pitch angle of something like 60 degrees.
Whoa.
And these are actually also similar to fun things that are happening in Saturn's rings. Things like spokes.
Okay.
Oh.
Weird fun thing. You don't like
You don't think spokes are fun?
Well, I mean, there are spokes in Saturn's rings. Yep. Yep.
Wow.
Yep. But I'm guessing that the underlying physical source for this thing is very different. Than, Yeah.
But in any event, so this is the cool thing. So this is in one of Saturn's. By the way, how many arms does our galaxy even have?
Oh, we're
in the Sagittarius arm.
Is this a bonus trivia? Can we answer?
You can try and answer.
I can try to answer.
Yep. That's what he said.
I will say there are 8.
There are
4.
5 arms.
5?
No.
There's no good answer.
Yeah.
There's definitely fewer than 8.
Yeah.
So for one, we still haven't modeled what the solar system or what the
there's 8 arms just in this room. So
there are really 2 primary arms.
Okay.
The 2 primary arms being the Perseus arm
and the Sagittarius arm.
And the
Stegosaurus arm.
The hilariously named
Scutum arm.
Centaurus arm.
Okay, I was like, I know it has to have something to do, if you think it's hilarious, it probably has something to do with male genitalia.
No, come on now.
So typecast. So typecast.
Yeah.
No, any genitalia.
Any genitalia.
Any stuff will be good.
Usually it's just, all right, okay.
Anyway, the Scutum Centaurus. But there are...
Scutum what?
Centaurus.
Scutum Centaurus.
Scutum Centaurus arm.
Yeah. There are some smaller arms as well. The Sagittarius arm is the one we're talking about here today, and that's it's a minor arm compared to those other 2. But so 2 would be an acceptable answer to the question: how many arms? But also 5, I think we'll give Eddie.
You're just making crap up now, though.
No, I'll show you a picture of this. I mean, I won't show you because
you can actually
is there an ombre effect?
Inside. We can't see those arms.
Can't see this. Anyway, we live in a kind of a spur of the Perseus arm called the Orion Spur. Which is close to this little mini thing called the Sagittarius arm, which has a pitch angle about 12 degrees or something like this. But we found a bit on it, a big piece on it that has a pitch angle of 60 degrees. Weird, interesting. I don't know. Maybe you're saying, why is that interesting?
Yeah.
Maybe like a giant Death Star flew by the galaxy and dragged those stars out at a funny angle.
Weird. Probably not. Is it aliens? Probably not.
Probably not.
Probably not. Okay. But it could be something like...
Maybe a rogue black hole drove through the galaxy.
Yeah, what was it, Jim?
At a funny angle.
No. I think one of the cool explanations for this is, and this kind of stuff does also happen in Saturn, I think, but in Saturn's rings, but if you get a conglomeration of mass, you get a big blob of stuff.
Yes.
Then
I try to avoid those these days.
As that is rotating around the thing, it shears, right?
Yes.
And so
that does happen in Saturn.
It does happen in Saturn. Again, in the spiral arms in our galaxy are going much more slowly, and they spin around. Obviously, like we go around the center of our Milky Way galaxy maybe 4 times in a billion years. Quarter of a million,
that's right.
or a quarter of a billion year rotation, and so it takes
Well, why do you get just this one blob? Why is there just one blob and one sheared thing?
Right. So there should be many of these things.
Okay.
And we're pretty sure there are, but of course, we're only going to be able to make out small scale structure in our galaxy fairly close by. So the Sagittarius arm is like the next structure inward towards the center of the galaxy from us.
Okay.
And this structure is like directly in line with the...
Now,
we're not going to see stuff on the other side of the galaxy and way out there.
In Saturn's rings, that angle that those... as you said, you get a whole bunch of stuff together and it wants to make a blob, but then the parts that are closer in are orbiting faster and the parts that are closer out are orbiting slower. So it stretches out, it makes this sort of elongated thing at some angle.
Yep.
And in Saturn's rings, that angle is about 23 or so degrees. And that's not really special to Saturn. That's, I think, just has to do with Kepler's laws. That sort of comes out as to what you get. I don't think that if you sort of change the mass ratio or something like that, that you get a very different angle. So the fact that this is at 60 degrees would say that it hasn't, it's like still sort of in some maybe transient.
Right. That could be. I mean, if it hasn't.
Or, or maybe the angle does really depend on what the mass of the blob compared to the mass of the thing that you're orbiting is, or...
Right. Remember, of course, I mean,
plus in Saturn, everything's orbiting, in Saturn's rings, everything's orbiting that central thing. Whereas in the Milky Way...
Right. This the thing is, the orbits aren't exactly Keplerian, right? In the galaxy, or at least not till you get very far away from the center of the galaxy. So, and this is not that far away.
That's interesting. But shouldn't we can we see this in the Andromeda galaxy? Shouldn't we be able to see this in other galaxies?
We should. We should. So you need fairly high resolution to see this. This is fairly small. So the size of this...
It's just a little bit of it that's got a kink, got a break.
So, I mean, I don't know. The kind of broken arm is what people are referring to. And but this is about 1 kiloparsec.
Okay.
We're mixing our units here, by the way. A lot we were talking about the size
3,000 light years. Anyway.
Yeah, 1,000 parsecs. A parsec is about 3 light years. So... that's fairly small compared to the size of the galaxy. That's going to be a little bit hard to see. And
but I'm pretty excited about this now because...
that's good, because he was not saying...
I was not excited earlier.
All right.
But now I'm pretty excited because I've done a lot of study of those sheared out blobs in Saturn's rings. Yeah. And I'm super curious to see if that's going on.
It's conceivable, of course, that this perturbation has a different... origin, but that's one of the leading candidates, and you're right, it is cool because it's just like the same physics as this happening. I think that's pretty cool.
All right, well, speaking about physics being the same everywhere but the numbers being different, how about that segue?
Great.
How fast can you walk on the moon according to theory and experiment?
So should we give two different answers?
On the Earth the answer is 4.5 miles per hour.
Okay.
What is it on the moon based on theory and based on Vomit Comet experiment with 8 volunteers on a treadmill? Maybe they weren't volunteers, they're probably paid.
I've been trying to think about this and trying to think about the physics involved and figure out just whether it's faster or slower.
Right.
And it's not that easy. I can't, I don't know, but maybe
intuition fails. Yeah. It's hard.
Which one are you going to
go? I don't have any intuition.
I'm going to say 2.3 miles per hour. I'm going to go slower.
You're going to go slower. I was also leaning slower. I'm going to go 0.5 miles an hour.
Wow.
Okay, Addie wins.
Yes.
Based on the
experiment, it's a moon question, Jim.
Based on the experiment, it's about 3.1 miles.
Oh wait, we're supposed to say. So that's based on experiments.
That's based on experiment. 3.1 miles an hour.
Okay.
Prediction number, higher or lower?
Prediction number was also lower. I would.
I'm going to ask you. I'm just asking you. Is the prediction number higher or lower than that?
Lower.
Higher.
Lower. Yeah, 1.8 miles per hour.
Really? That low?
So it's harder to walk fast on the moon, but easier to run.
Interesting.
I mean, mess these numbers up. It's definitely much slower.
It's slower, yeah. Slower. I mean,
I'm happy that we got at least the right direction.
We did go the right direction.
Win for both of us, even though the
I'm fine with that.
Is yours.
I'm fine with that. Yeah. I mean, like, if you think about watching the videos of the astronauts, and part of the reason they had so much trouble was their suits, but like also it's just really hard to like get a good... I mean, you don't have like traction, right? Power walking, they're doing these like it's really specific steps, and they're wiggling their hips, and then you have to do like this really specific. I don't know. There's a lot of like using the friction of the ground,
friction, right? Yeah, because friction is proportional to your weight, and your weight is much less, and so you don't have a lot of friction.
I mean, part of what I think is it's impossible to walk on the moon almost. Like we've been in lunar parabolas on the Vomit Comet before, Addie and I have, and it just makes you feel like. You can't. You as soon as you push, you're flying.
Yeah, it's very easy to
really
go forward.
Walking,
yeah,
you're bending.
And so it's. Yeah. I would say 0 miles per hour would be my answer.
I mean, it makes sense then that the prediction was so low. Yeah.
Well, it may have felt like a very slow walk on the moon. It was just another episode of Walk About the Galaxy. Give us 5 stars, and we'll transport you for 50 minutes to a long time ago. And galaxies far, far away. Be sure to follow us on Facebook and Instagram to get all our updates. And check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walk About the Galaxy, where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Production assistance was provided by Diego Rodriguez. Thanks to our listeners in Ireland and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the Astroquarks, signing off until the next episode of Walk About the Galaxy.
Congrats, Tracy and Chris.
Hammering.
And the newest little Astroquark.